Good evening, ladies and gentlemen. You are all very welcome to this Cockcroft Rutherford lecture. And this indeed is an event that is really the flagship in the calendar of our Alumni Association, and a very important event also for the University of Manchester. We're very grateful to you all for coming today and indeed for your further support for the university across the year. And you as our alumni are extremely important to the future of the university. We value your support, we value your thoughts, and we value your input. The university's goals can be described really in a sentence of virtuosity for global benefit. And so it's appropriate that two real virtuoso academics and thinkers from our most distinguished alumni, Sir John Cockcroft, and a former member of staff, Nobel laureate, Lord Ernest Rutherford, their names commemorate this lecture. I'm delighted to welcome some of the family of Sir John Cockcroft, Christopher Cockcroft, his son, Reverend Canon Catherine Milford, his daughter, and Peter Cockcroft, Sir John's nephew, who is also a Manchester graduate in textiles, who's here with his wife, Susan. I'm afraid that the lecture this year caused a significant amount of disappointment. The reason is that we offer first tickets to our alumni, and then once they've taken however many they wish, we offer them to our staff and students. I'm afraid on this occasion there were no tickets left to offer to our staff and students. And unfortunately, a number heard about the lecture and demanded to know why they couldn't attend, which simply means that Andre will have to give another one on some occasion. There is no doubt that the popularity of the lecture is down to our lecturer, Andre Geim, who I'm sure every one of you know shared the Nobel Prize with Kostya Novoselov in October 2010. Andre was trained in Russia and then took a number of positions in different parts of Europe before taking up a tenured position in the Netherlands. He joined the University of Manchester in 2001 as Professor of Physics with his wife and collaborator, Irina Grigorieva, who's here tonight with their daughter, Sasha. He was shortly followed by Kostya Novoselov, who is also a professor here in Manchester and had trained with Andre. And it was during those early years in Manchester that they undertook a number of groundbreaking studies leading to the publication of their seminal work in 2004 on the properties of graphene. Andre joined the university as a professor. He was then an EPSRC fellow, and last year he was awarded a very prestigious Royal Society 2010 anniversary chair. He also holds the Langworthy Chair of Physics, which is interesting because that was a chair also held by Rutherford. And indeed, he's the fourth Nobel Prize winner at Manchester to have held the Langworthy chair. This was endowed in 1874 with a sum of £10,000, today worth £800,000. But I think you would agree that would still have been worthwhile for the value it yielded for the university. Andre has many accolades to his name, and he is indeed the only Nobel Prize winner who has also won the Ig Nobel, which you may hear a little about. In 2007, he was elected a Fellow of the Royal Society, and last year he was made the equivalent of a Dutch knight. But of course, the real accolade and the great news for the university was on the 5th of October last year when we heard that he and Kostya had won the Nobel Prize for Physics, the first Nobel Prize in physics to the United Kingdom for nearly 30 years. And those of you who watched some of the clips and heard some of the stories will hear Andre say that he was as unfazed as normal and that he would continue with his normal day's business and thereafter. In fact, I think it was somewhat disrupted. But nevertheless, since then, in spite of the many, many invitations, the fantastic Nobel celebration in Stockholm, our own celebration and much more, he has continued to make major discoveries published in some of the best scientific journals. So we are truly privileged tonight to have one of our own current Nobel Prize winners to give this very important lecture on Random Walk to Graphene. Andre, I'm delighted to invite you to give this year's lecture.
Thank you very much, Nancy. Do you hear me? Okay. No, it's okay. So, yeah, very kind of you. What I will try in the next 40 or so minutes will answer two questions, because whenever Nobel Prize or other accolade comes around, people usually ask only two questions. Okay, how did you get it, and why did you get it? So first I'll tell the story behind, and secondly I'll try to explain what's so special is about graphene. So that's the story behind. This is my life path trajectory, rather random, rather diffusive, I would say, but I'm not a megalomaniac, so I will not show you pictures of my childhood and so on. So I think because it's quasi-scientific talk, I'll start with my PhD diploma. As you see, it's a Soviet, hammer and sickle there. Tells you that it's Soviet times. And the only thing I like to mention, the title of my PhD. It reads Investigation of Mechanisms of Transport Relaxations in Metals by a Helical Resonance Method. Does it sound exciting for you? Let me assure you that it was as exciting as it sounds now. But every cloud has its silver lining, and the message I got from my PhD was that try not to be too boring to yourself and try not to bore your students and postdocs and collaborators. Well, after PhD in 1990, somewhere at that time, I have become a staff scientist in Moscow and need to find out my own research niche and trying to do something new. What we had at that time usually were shoestrings and sealing wax, and sometimes I managed to find an old shoe somewhere around, and with the help of those things, try to make my scientific work. And combining those things, I managed to progress a little bit further. The message I took from that time is that even if you have as little as this one, and not everyone scientists in this audience, probably most are from different walks of life, but you still can combine and never give up, whatever your project is. Combination of what is available is a really powerful thing in this world. So it was 1990, and at that time, even sealing wax was in deficit in Soviet Union. So I looked for greener pastures. And 20 years ago, at the age of 32, some people in this audience are younger, I had HIndex 1. Most of you who are not scientists don't know what HIndex is. So let me put it this way. If you have an HIndex 10, you probably have a chance in an academic world. If you have an index 5 at this age, you probably have to find another job. If you have HIndex 1, it's probably crème de la crème of the losers. And still, I tried my chances at the Western market, and over 4 years I traveled in different countries and different universities, and I learned plenty of different things. I don't like to be very specific. Those slides are from my Nobel lecture, but I tried many different things because there were several universities involved. One story I like to tell you, that my very first visit to Nottingham University as the Royal Society visiting fellow was for 6 months only, and it's very hard in such short a period of time to do something reasonable. So when I come to my host and ask them what to do, they found some devices in a drawer which was done and dusted long time ago, say, you measure, hoping that I will fade away for the next 6 months. So fortunately, because I had this experience of combining different things and so on, working on a shoestring, managed to publish decent papers, and then, okay, this propelled further and further, and the experience I took away, which unfortunately many of my PhD students and colleagues suffer every week, when they complain that samples do not work, I usually pronounce philosophically that there is no such thing as bad samples, only bad postdocs or PhD students. It's with a smile, of course, but they don't take it with a smile. So after those four years of working, HIndex was high enough to get a reasonably high position, which would be reader or senior lecturer in Nijmegen. And the first thing was, again, trying to find the niche, try to do something new, and there was maybe not a shoestring, a sealing wax, but it was very little available at that time. So again, I used my previous experience combining structures from England, lithography from Russia, and making devices from Russia, and measurements were done in Nijmegen. For people who are familiar how quality of the papers counts in physics, those are very prestigious publications. So it was hard time, but by 1997, I felt myself good enough trying to look for something else in addition to my everyday research. Something turned up which people these days call Friday night experiments. I'm not sure how this term came around, but presumably one Friday night I did one of those experiments which led to a serious one. So what we had in Nijmegen in the Netherlands were Asian magnets. They consume a lot of energy and were very expensive to run. But scientists sometimes, like bankers, they say, if you don't give us those many millions, our expertise will disappear somewhere abroad. And when those millions are given, they suddenly find out that they don't know what to do with those facilities. They find out. So I felt pressure associated with this magnet that we need to do something with those. And I looked around what could be done in high magnetic fields at room temperature. Not much has been done before, but I stumbled on a phenomenon which is called magnetic water. You know that if you put hot water through tubes, there is scale on your kettle and something like that. Then if you go to, say, DIY or go on internet, you'll find out that people say magnetic descalers, which is essentially a small magnet you put on the tap of your water tap, and by magic the scale disappears. At least people say so. I have no comment about this. Try to understand whether it works or doesn't work, or just completely random, whether this is true or scientific fantasy. So, but apparently this brings me to a question. If this is a small permanent magnet, what would happen with water if we put it in high magnetic fields? 20 Tesla, it's a very strong magnetic field. This sort of facilities exist probably in 10 places around the world at room temperature for long years. So one Friday night, I took a bottle of water and poured inside this vertical ball of the magnet. For those who are scientists, or at least did their PhDs, they probably know that pouring more water inside your equipment is not a very scientific sort of experiment. And I try to justify it in retrospect, why did I do this, but have never find a good explanation for doing this. Okay, so essentially, instead of water appearing somewhere at the floor, I found out that the water levitates. Okay, it's a shining green laser. It's about 5 centimeters in diameter, 3 centimeters or 5, this ball of water. It took probably an hour to understand that phenomena behind is well known. So what was not known and what was shocking for me and all my colleagues later is that magnetic fields, which existed everywhere in the world, okay, strong enough to cause this phenomena due to this well-known, cause levitation due to this effect. So scientifically speaking, it was not much of a discovery. It was, okay, I find out that it's very therapeutic to look at this, at this one. Very nice images, but it was a shock for your intuition what magnetic fields could do, and my colleagues came with brilliant ideas what else could be levitated in those. We tried many, many things. After some time we got fed up with what to do, so it requires, because everyone asks, and this can levitate. So placing emphasis was becoming important, and we put a frog, a live frog, inside a magnet, and this is a movie, 1 or 2 seconds of levitating frog inside there, and then it hit the public life. And God said, and everything levitating, boffins, and so on, and it was people say Nobel Prize experience is a lot of a public of events, and that was really when I suffered from the media. So frog has made even into the politics. Guardian came up with this phrase, if frogs can fly. I do not claim that Tony Blair won his prime ministry due to the frog, but apparently it was an interesting experience. So, but behind this noise and media coverage, okay, what happened that the picture of the flying frogs appeared in many textbooks. I normally go to a conference, a big conference from, say, physical society of some country, and people say, oh, hello, I know you. Forgive me, I don't know anything about graphene, but I start my lectures with showing this picture of flying frog, and students always interested to learn how did you manage to get that. And this is for the first time I got my fan mail in my life, and I still keep this lecture. Could you send me some information about your feather? I'm 9-year-old and I want to become a scientist. Jennifer Miller. So very nice to have this. So I think I rest my case about the frog here. So, okay, it was time to move on, and 10 years ago, only 10 years ago, I got chair in Manchester. It was not as smooth sailing as one can imagine. Actually, it was pretty dilapidated lab space and reasonably small startup and no central facilities. But what? I got this experience before, and yeah, I need to establish myself, and again, combining different facilities from around the world, okay, we start publishing papers. Publishing papers brought research grants, and research grants get more and better papers, and so on. So within 3 years, we get well-equipped lab and state-of-the-art of microfabrication. Sometimes I go for a conference and try to, people make offers already for many years and so on, and I describe this Mancunian experience, frankly speaking, and say, would it be possible something like that in your university, and etc., and no one believes that it's even in principle possible, and it's really a very short period of time. So the country and the university were very kind, I would say. And probably my previous experience was fitting very well into the funding system within the country and the university. So thank you. Yeah, 2003, okay, once try to cycle, you never stop it, okay? So in 2003, I started thinking about what else can you try away from your ordinary line of research. Probably the previous experience was so extensive that I know long after the frog story, I was afraid of making fool of myself, okay? Of course, I did many times, but okay, yeah, that's how it works. That's magnificent animal, and what I learned from literature, the mechanism behind this climbing ability of geckos is very simple. Their toes are covered with tiny hairs, like your beard, but millions of those hairs together. When you have one hair, it sticks to the opposite surface with minute force, but millions and billions of hairs working together, they create a formidable force enough to keep geckos on glass ceiling and so on windows. So what was most important for me, that the size of those hairs is not like in your beard, but okay, of some micron size, exactly the same scale I'm working routinely in my research on more complicated things. So that's what we try to do. One Friday night, of course, it took many, many nights and so on, and we proved that it's indeed possible, making a very small patch of this hair. It turned out to be a very important proof of concept. It's still not on sale, but a huge community of people dealing with adhesives are interested in this research and trying to prove this. So I would love to produce something like a Gecko glove and let especially some students out of the window to climb, but unfortunately we had only 1 square centimeter, and all we could demonstrate a Gecko man essentially placing their emphasis. So that was another successful experiment, and then people saying, all right, I listened to this lecture, now tomorrow I go to my lab, and tomorrow is Friday, and I'll try some experiment. It doesn't work this way. Usually, okay, there were many, many failures and so on. But preparing my novel lecture, I actually tried to count those. And I have found that I actually had time for 20, maybe 30 experiments which were out of the trodden path, okay, a little bit mad if you wish, and 3 of them worked. So the success rate is 10%, and I'm still trying to mull over this experience, okay. The failures are not as often as one could expect. So I don't think that my ideas were particularly good. I think more important is whatever walk of your life, if you try to step away from your trodden path, you're likely to fail. But these failure chances are not as high as we perceive those. So I encourage everyone in every walk of life trying to do something away from their path. So that comes me to the last successful, okay, or at least last famous Friday night experiment, which led to the Nobel Prize. So usually people refer to the first experiment we did like Scotch Tape experiment and Scotch Tape method. You will see why. So 2002, I got my first PhD student. I got collaborators, my wife, and Kostya Novoselov, who came as PhD student at that time, as a postdoc as well. But that was the first PhD student. I needed to invent a project. So I just said, okay, there is graphite. It looks like a very new and interesting material. No one has made thin films out of this material, which I looked through the literature indeed. Let's try to do something, make graphite as thin as possible. and see what properties this thing will bring. So I bought for £200 a tablet. Research is expensive. So for a tablet of graphite like that, 1 inch in diameter, and said, okay, that's your PhD project. Try to make thin films out of this, and if you'll succeed, we'll study. So 3 months later, Da, a nice Chinese student with not very fluent English still, brings me this Petri dish with a tiny speck of graphite at the bottom. I look at this speck in a microscope and saying, well, that's too thick. It's not 1 micron even, it's 10 microns. Try to do something thinner than that. And he tells me, can I get another piece of that? You can imagine my French at that moment, yeah. But at the same time, there was another guy, another postdoc present, Oleg Shklarevsky, who told me, why do you use polishing? Look, that's what happens. We routinely use Scotch tape to peel the top layer and leave a nice surface. It's a routine technique to prepare samples for scanning, tunneling microscopy, and other sort of scientific analysis. And we always have thrown this Scotch tape away. And he digged it out from a litter bin nearby. I looked at it and, oh, that's pretty thin, much thinner than this one, for sure. So looking through the tape, the light comes from the back. You really see that some pieces are even transparent. You can do it at home. This piece is probably less than 10 layers thick, and we know now, not at that time. And that was, okay, a very sort of important moment. I long-lived Scotch tape from that time for the last, okay, still we are using similar, very similar technique, maybe not Scotch tape, but a sticky tape to do that. So essentially, it took a few months to go to a single layer. You'll see it's better on its atomic force microscopy pictures, the first published one for graphene. Better images comes later. And then it was not important to only observe, but we start studying properties, making devices, and seeing what sort of properties this material have. So, and after a lot of work for 9 months, it was probably not 24/7, but it was probably 18/6. So we publish a paper, which is in Science, in a very prestigious journal, and it's quoted in the Nobel whatever release prize as the paper which opened up the field. Irina, my wife, is here. Kostya Novoselov, my co-prize winner. Da Zhan, who runs a making graphene company with this experience, is here. And this is our regular visitor in this university, still around. 5 out of 8. So what you can learn from this experience, that equally top layer journal rejected our paper twice, and one of the referees gave his insight that paper offers little new insight of those. So I think whatever, if you are a scientist and your paper recently was rejected, you can always hope that it will be a Nobel Prize winning paper. But for those who are not scientists, they also submit their projects to their supervisors and peers, and if they are rejected, take it with a pinch of salt, opinion of your peers. That finishes my first part, how. That was my random walk. And in the second part, I'll try to explain. It's more, okay, it's shorter, but it would be more scientific. a little bit, but don't be afraid. I'll try to explain in something why. Okay, so let's look outside this building on the Oxford Street. You can see many things over there, a lamppost, a tree, your colleague maybe, and yeah. What all those things and people have in common? Everything around us has length, width, and height. And what scientifically speaking, everything is three-dimensional. You won't find objects or materials which would be only one atom thick as graphene. Why this is so? This is very fundamental. We live in a three-dimensional world, and everything usually comes by self-assembly of molecules, as it's shown on this movie. Everything tries to merge together if temperature low enough, and then you get pieces of materials which with this vibration, they eventually all go into a three-dimensional form. So the nature is so smart that whatever you try to do, the nature tries, why do I need to use only one or two-dimensional space? All this three-dimensional space is available, so I'll try to construct something in three-dimensional space. So growth, making in natural way, it's strictly forbidden to make one atom or lines or flat things there. So what essentially we did with this Scotch Tape technique, we took a three-dimensional material and pulled out an individual atomic plane. No one has done this before. It seems to be so trivial and simple, but somehow assumed to be impossible or next to impossible and so on. That's how graphene looks like on a substrate. It can be in freestanding space, but on substrate, what you see here, the first, two-dimensional material, one atom thick, and it's a crystal. As crystal as diamond is. It's a perfect crystal. Shape is not perfect, but the structure is perfect. So what's so special about this material? We know that it's one atom thick, but it has a very simple structure. It's hexagonal structure, and that's it. It's so simple, you don't really expect many wonders out of this material, and except for that the thinnest imaginable material, if it would be only this one, no one would give the Nobel Prize for sure. So, but there is a long list of superlatives to this material. So, of course, it has the largest surface area. 1 gram is able to cover the whole Trafford United football pitch and the stadium as well. It's a huge surface area. So it's also turned out to be the strongest material ever measured until today. It's stronger than diamond. It's also stiffer than diamond, but at the same time, it's a little bit like rubber. You can stretch it, and in addition, it's very pliable material. So it's very unusual how it behaves. It shows record conductivity of heat, outperforming diamond. It can sustain current, which is 1,000,000 times more than copper can do. Imagine cables made out of this material, if ever made. It's, despite being one atom thick, it's completely impermeable for any liquid of gases, which is also something which you don't expect. The most interesting is its electronic properties. I'll mention about this a little bit later. Those superlatives get a little bit too boffin-like. So you can imagine the first question usually people ask, what can you do with this material? And you can imagine, because it's better or best out of those, you can imagine some applications coming of this one, despite it was only a few years. So when speaking of applications, and because I'm mostly involved in fundamental research, I like to tell you a story about dolphins. Okay. So once I was, once I was on a boat trip watching dolphins, and not this particular school, but they were wild dolphins, and at the same time they were very friendly, looking for a human touch rather than begging for food. And imagine people, 20 or so on board, and everyone at awe. Fantastic, romantic moment. It lasted probably for a couple of minutes until a little boy in behind suddenly shouts, "Man, can we eat them?" So that's a very subtle balance which are in universities and in academia is between a romantic and a chancellor. Okay, let's put it this way. I personally try to keep the balance and to please those who think different ways. Okay, you actually have to study whether those animals are edible at all. Actually, I tried once this joke in Japan, and you can imagine the reaction. There are plenty of applications. It would take many transparencies even to overview those. Some are very fine future, and some already happening, like conductive ink and batteries. Okay, I have no time. Just let me say that George Orbisbaum already gets tax on this research, from this research. I'll give you two examples to be specific about this. It's ultra-high frequency transistors. Okay, we speculated about those already 7 years ago in our first paper, but nothing was happening for around 5 years. And then US military suddenly put a lot of money into a single-minded program to make these transistors on sale within 5 years. Why do you need those transistors? You probably know how much frequency band costs for billions and billions for telecom operations. You can't, and there is a terahertz gap. It's called gap because there is nothing is operational there. We don't have devices, we don't have detectors, we don't have anything to go there. It's between those high frequencies mobile operators are using and infrared frequencies where detectors are also developed. So people were thinking how to utilize this for communications mostly. So it looked completely unrealistic, even for me at that time. But yeah, within a year, people showed, okay, that it's possible to make 100 gigahertz, already quite enough. Last year it was 300, and academically speaking, it's all done and dusted. It remains to be seen whether military can do something with this, and then as an outcome of this military research will benefit from high-frequency communications. It looks promising as many other areas of research. That's another example I like to bring it. It's also very close to industrial applications. ITO, it's indium tin oxide. If you have a computer screen or your mobile phone, you need light coming out. To come out light, you need something transparent and conductive. Indium tin oxide is transparent and conductive, and graphene is also transparent and pretty conductive. In addition, graphene is flexible, and this is one of its advantages. So the idea general, which is probably came initially from us, from our group, is that instead of all those devices, okay, instead of ITO, put graphene on a polymer film, and then you get the same devices but bendable and foldable. We demonstrated as academic research only 2-3 years ago. It was for fun. Mostly, we didn't really thought that it's feasible, but okay, a year ago, Samsung researchers have shown that they can produce reasonably cheap, actually comparable with ITO prices, a huge screens of graphene, and then it becomes pretty realistic to use this in those devices. So I'm not in the business of advertising Samsung, but that's the advert. Similar advert is done by Nokia. You can find on the web. This is how they see the future of gadgets in the way that's, of course, very futuristic, but they put a lot of emphasis on graphene. So the message I like you to take away, despite 6-7 years, it's actually a record time for any material to go from academia to industry. And it's already in some products these days, and more probably to come. So, but coming back to the dolphins, actually, in my walk of life, I mostly study fundamental science. I'm a romantic with an eye on applications, if you wish. So I'll give you an example how very special this material, and this is not for applications, but for fundamental properties of this material, a short overview why the Nobel Prize was given. In materials, you probably know, some of you at least, that there are electrons and they move like bullets, or more accurately like waves. And we know how to describe. We've perfectly described materials by some simple equation, and everything else comes on the top. If you are not a material scientist, but a particle scientist or astrophysicist, you usually deal with another completely different equation, which is called Dirac equation, and movements of particles is very different. So what graphene brought to us, electron waves, which instead of being like that one, they really mimic what's happened in ultra-relativistic world. And you can imagine that on the basis of this material, you can test some predictions which are valid for, say, particle physicists and CERN and so on. And I'll give you a couple of examples. That's a simplification of phenomena which was known for 80 years, but presumed not to be possible to be tested in any accelerator, so hard to design this experiment. That's what happened with your car if you drive into the wall. But if you would be really small, like an electron, you can, in a quantum car, the ghost of this car would go through, or part of this car would go through, not a bumper, I mean, but a sort of possibility of car to tunnel through the wall would be. In graphene car, if you are driving, what's happening, neither like those two, because it's ultra-relativistic particle physics world, the car goes through without noticing this wall. And that, as I said, was presumed not to be testable, and that's phenomena which we easily observe in graphene using electron waves which propagate inside. This phenomena actually another example of fundamental physics which you can do in your kitchen. So what we, somewhere 2-3 years ago, we cover an aperture with graphene. That's a light shines through. It goes completely here. That's a single layer of graphene, and you see some opacity. If you test it, you'll find out that opacity, you can just see graphene. If you put it on a window, it would absorb 2.3% of light, which is an enormous amount for only a single layer of graphene. And it's very unusual. What is enormous absorption? And could lead to some applications. What is more unusual than when you try to analyze what does it mean, you'll find out that this opacity is just given by pi, this circumference of circle, multiplied by the fine structure constant. Fine structure constant, it's probably the most mysterious, 1/137. Probably everyone heard about this constant and how unusual it is. So in this experiment, in a kitchen, you just look at this transparency of graphene and find out that what you probe, relativistic physics, you'll find out what the coupling constant or fine structure constant is. So another one is probably also one of many phenomena which is easy to understand how fundamental it is. It's the periodic table implications. You know that there are something 100 or so 116 elements available in this world, some of them stable and less stable and so on. So the question you would like to ask, imagine some nuclear physicists make a nuclei which would be 200 in mass. Would you get some super heavy material like sometimes described in science fiction? The answer is actually no. This model of Bohr model of atom is valid only when you forget about relativistic physics. If you really have a heavy nuclei, you'll find out that your super heavy materials would be not unstable because the electrons would fall on the center. This phenomenon known for 60 years, but no one was able to probe this phenomena even in principle. In graphene, the coupling, the interaction is described because by a different constant, and this phenomena is possible and currently is probed in different experiments in graphene. So we can do something what people in other walks of scientific life couldn't do. So where it brings us, okay, so to give you an idea, this area usually Nobel Prize closes the area of research. That's a very hot area. So I'll give you an idea, for example, where we would like to be. 5 years ago, we have shown that not only graphene can be extracted by this Scotch Tape technique, and of course mass production can also be done for other materials. So some of those materials are different from graphite, some insulators, some ferromagnets, some superconductors. Everyone deserves some attention. Maybe some would be equivalent to graphene, maybe not, but remains to be studied. But what I really like to do is to see what sort of materials you can make by this Scotch Tape technique. Something like that, okay. And if you make a material like that, the question is what properties could be of this material. So it's a huge possibilities in future, and I hope I'll persuaded you that there are many phenomena and they're far from being exhausted. And this is so far mainly about science, but applications are really coming. So let me finish with my last slide. If you have a pencil and draw a line by this pencil, you see a dark trace. Dark trace is pieces of graphite from the pencil lead, and they're usually thick and contains many layers of graphite, like the speck Darjan, my PhD student, made. But if you take a microscope and look carefully enough into this pencil tray, and we did it, you'd certainly find a single layer which brought the Nobel Prize. So my message is that actually how shockingly little we know around the world around us. Thank you. Thank you.
They say that a good talk is about storytelling, and what a beautiful story, wonderfully told. Thank you, Andre.
Thank you.
Andre's agreed to take a few questions from the audience. Can we get the lights on the audience so I can see where you are? And we have some roving microphones, so if anybody has a question you'd like to put to Andre. One there, just next to you.
Thank you very much. It was a very, very interesting talk. I very much enjoyed it. Some people are defining graphene as maybe up to 10 layers, or 10 single layers, whereas I normally think of it as being just a single layer of carbon. What's your view on the nomenclature and whether or not graphene is strictly a single layer, or whether it can be this rather more arbitrary thing where maybe you've got up to about 10 layers?
Yeah, so the question is what is graphene essentially, whether it's a single layer or not. So there is a system which is called bilayer graphene, which is two-layer graphene, and there is so also a term which is called few-layer graphene, which extends to anything up to, I don't know, 10, 30 layers. So my take is very simple. It's you have to compare what is a grain and what is a pile, where it starts. For the case of graphene, 2 is already a pile. If you compare chemical properties of graphene, 1 layer is possible to easily functionalize, say, with fluorine, hydrogen. It binds from both sides. And chemically, it's much more active than 2 layers. 2 layers already behave more like graphite. Electronic structure, it's completely different. And most obvious, for example, mechanical properties. If you put a single layer, the only way to destroy it is to tear apart. And it's as strong as diamond, stronger. But when you put 2 layers, they can slide against each other. So it's really single layer is unique. Other systems, few layers, also interesting, but it's another material altogether.
Question down towards the front here.
My question relates to the fact that your talk was superb. I have nothing but endorsement for the gentleman who preceded me in saying thank you. However, one of my colleagues at Manchester Materials Science helped you with some electron micrography. The back end of last year, I asked for a picture that he'd taken of your graphene. His name is Peter Kenway.
Yeah.
He said he didn't have any micrographs, so he couldn't copy one to me. Can I give you my card with his email address?
Okay, well done.
Thank you.
Okay. Thank you, Peter.
Any further
Yeah,
questions?
okay.
One there just behind you.
Graham Cliff, okay, thank you.
And then there's one
Just
right
a
down
short,
front.
a short question, if I may. Sorry.
Andre, up there.
Yeah, that's...
Yep. Yes, go ahead.
Okay, yes, a very short question, Professor. How temperature dependent is the strength of graphene? Is there a limiting temperature at which it is less strong?
Yeah, all materials eventually melt, but strength of graphene remains very high until at least 1000 centigrades when the material was probed. One of superlatives which I didn't mention because it's not really confirmed by many groups, but there is a claim that graphene has the highest melting temperature of 5000 centigrades, more than graphite or any other material. So until it's very close to the melting temperature, it remains a strong material.
Question at the front down there.
Would you by any chance be looking into researching into graphene as a constituent component of a superfluid?
Superfluid. We have boffins, not only myself here. I don't know what to answer. It's a material, and to be a superfluid, it first to have to be a fluid, and it's a solid. Okay, so people are looking for superconductivity in this material, and people are, including ourselves, and people are looking for excitonic superfluidity within the material. It's a very hot research subject, but there have been no reports yet.
Thank you, Professor, for your speech, lecture. Does graphene have any applications for solar panels?
Sorry?
Does graphene have any applications for solar panels?
It's widely discussed in literature. The answer is it's not clear yet. Okay, so it's for solar panels you have to have a transparent and conductive material, which graphene is, but the requirements are very stringent, and maybe at least now graphene is not as good as, say, ITO of high quality. But people are talking about variable solar panels, where to put it on your clothes is something cheap, and some using polymers and so on. So it's widely discussed as inert flexible material, maybe not with the efficiency of silicon or other solar cells, but sort of one of niche applications.
Yeah. Thank you. It was a superb lecture. My question is, when that little while ago now that you asked your PhD student to actually get a thin layer of graphite, 1 atom thick, did you have any ideas about what properties it might have? What were your best estimates of the properties at that time out of the whole list that you presented later on?
That's a very good question. Okay, yeah. When we're trying to start any new research area, it's I start whether not what this should bring, but whether this system has been exploited or explored sufficiently. What I was sure that thin films, saying 100 layers thin, were badly exploited, and that was a new system which I wanted to explore, that it went down to a single layer was an additional benefit. So there is this tendency, which is actually described in my novel autobiography by many PhD students and postdocs and senior staff as well, to study literature ad nauseum to figure out what has been done and what is not. If I would be doing the same, I would never start research. Okay, there was a very superficial look through the literature and finding out that it's reasonably good. I just to get on the bike and try to see how it behaves. Okay.
Question over here, I think.
So graphene's got very good conduction properties, in like net transport properties. Do you know if it preserves phase information as well? Could it be technically used for perfect state transfer or?
I didn't hear. Can you say it again?
For perfect state transfer, is it just net transport properties that are good, or does it transport entire states?
What sort of net transfer? Sorry, I don't see you. Can you raise your hand?
Sorry.
Where are you?
Is it the total amount of electrons that are conducted? Does it preserve the information about those as well?
About electrons?
Yes, about like the phase information. Or...
Does this relate to the car?
Yeah.
Ah, okay. I think what the question, I think the question is asking that when electrons pass through, do they do so randomly or do they retain any sort of relationship? Is that right?
All right, okay. Yeah, that's actually my area of expertise, electronic properties, and put in this way, electrons shoot through graphene as bullets, but without any mass. And actually, they can shoot distances at room temperature as large as 1 micron, which is probably thousands and thousands of interatomic distances, which no any other material has ever done before. That's unique electronic properties of this material. They shoot like straight away this many applications are based on this principle that they're ballistic transistor, high-frequency transistor, and so on. So in some experiments, we really can show that, okay, distances is not a problem for those electrons. And this relates to this unique electronic structure of the waves. Yeah, thank you.
Okay, could I invite Janine Watson, who's president of your alumni association, to just thank Andre on your behalf?
Well, I think I have the most pleasant job in the room tonight, thanking Andre on behalf of all of us for that lecture. I have just taken over as chair of the Alumni Association, and I think it would be appropriate to say, first of all, to my predecessor, Andrew Spinoza, thank you very much for the 6 years that you've led the association. I think you've put us in a position of strength. We're one of the most effective associations in the country, and I hope we keep the relations and build relations with all of you as the university moves forward, and very grateful to the university for supporting us. So, Andre, we have here some tokens of our appreciation for that lecture.
Thank you very much indeed.
How inspiring it was.
Should I open? Should I open?
And I would like to say, on behalf of all the arts graduates in the room, if we'd had physics teachers like you at school, we'd probably all have stuck with it after the GCSEs and the cathode ray oscilloscopes. So it was inspiring. It was wonderful to hear about your groundbreaking work, and it makes me very proud of the university and very proud of the city of Manchester. So on behalf of everyone in the room, on behalf of the 240,000 alumni around the world, thank you for the work that you're doing. It's absolutely fantastic.
Thank you. Thank you. Thank you. Yeah, thank you very much. And yeah, I'm not sure that every PhD student and postdoc would share your opinion after listening for 3-4 years of my continuous teasing and mocking and so on. Yeah, yeah, okay. So yeah, okay. I would.